So welcome all of you to today's distinguished lecture series. Today's speaker is Professor Vivek Datar. By the way, for all the new students here, my name is Murthy. I used to be in this institute long time ago, and I was requested by the organizers to come and chair the session today, chair the talk. So, yeah. So, it's a short introduction to Professor Vivek Datar. He is presently a Rajaramana Fellow at the Institute of Mathematical Sciences here. He was earlier project director of India-based Neutrino Observatory project and a senior professor at Tata Institute of Fundamental Research. Before that, he was the head of the physics division at nuclear physics division at BARC. He was a couple of years junior to me in BSc honors, physics honors in Bangalore, and he joined the training school in 1974. So he has had a very distinguished career over nearly four and a half decades now, and he has been, there are various things here, it will take me a long time to read it, but I would like to make some personal remarks. I knew about him indirectly through Professor CVK Baba, who is a kind of mentor to large number of people, including many people in this institute, and was a very good friend of mine. And Vivek Datar worked with CVK Baba on many experimental projects. Though he was not his official guide, actually he did his PhD and later his research with Professor Baba. I heard about them in the 90s when there was a bit of controversy which was actually settled by the work of Vivek Datar and Baba. And that was about the discovery of 17 keV neutrino by John Simpson. Actually, John Simpson was a well-known experimentalist and well-respected. So when he claimed the discovery, it was a very serious thing. And it was shown by Vivek Datar and CVK Baba et al. That actually there is no particle at that, there is no neutrino at that energy, 17 keV. They were the first ones to show that, and later experiments, other experiments followed and showed that the discovery was anomalous. Actually, it led to another development about the detectors, because it had the actual anomalous discovery was due to some not so well understood fact about solid state detectors. So he has also worked on axions. So you will see in the talk today that he has worked in atomic physics, nuclear physics, high energy physics, and astrophysics, polymath in a real sense. And he's a kind of theorist's delight. In fact, this can be attested by many of my colleagues, including Indumati here, that he's open to many ideas. In fact, he never dismisses an idea, even if it comes from a very theoretical minded person. So in fact, when Professor Rajshekaran and I wrote a paper on possible discovery of dark matter at Kolar gold fields, he was the one who took up the idea and then started looking at it more seriously and see what can be done in the underground neutrino project. Then later on, when we were talking about if there is any difficulty in constructing an underground project, is there any possibility of doing it on the surface, then he thought of the Veto detectors, and then R&D on that is still going on, and possibly it may become a reality too in the near future. Then he has also looked at the possibility of discovering monopoles, signature for monopoles, dark matter, and also he was part of the collaboration on neutrinoless double beta decay, etc., etc., some of which he will talk about today. So basically the point I wanted to make is that he's a one with wide interests and really takes up ideas which are challenging and not a routine run-of-the-mill experimentalist at all. So you will hear at least part of it today. So Vivek Datar.
Thank you, Murthy, for this kind introduction. Yeah.
Just a quick announcement. This talk is being streamed live on YouTube, so YouTube audience can ask questions through the comment section. We will take it up at the end of the talk. Thank you. Over to you, Prof.
I don't know whether I will live up to all that Murthy has said, but I will try to, give you a flavor of the things that I have been involved in. Also, let me take this opportunity to thank the organizers, in particular Arijit and also Professor Ravindran for inviting me, and I was of course very glad to accept. It's an honor actually. Okay, so let me start right away. So this is a kind of, by the way, I should also say that I had given a choice to Arijit, one slightly more technical talk on a limited topic of underground, what science can be done in underground laboratories, and this topic, and he chose this one. So if it doesn't go too well, he is the one to blame. Okay. So anyway, so I'll talk about my early years in Van de Graaff laboratory in BRC, then a little bit of an excursion into atomic physics, and this was of course due to my teacher CVK Baba. Then of course experiments at the 14 million volt tandem, because of course when you have a big facility like that, you have a duty to do experiments there and think of some good ones too. I guess some of them were reasonably good, I guess. Then we worked towards an underground laboratory for measuring atmospheric neutrinos, but also some of the other things that can be done there. And this of course is continuing because we still don't have the site. So anyway, and then some thoughts on future outlook. Okay, so just one slide on my background for you. I did my schooling and college up to BSc Honours in Bangalore, as Murthy said. So I graduated in Bangalore in 1974. And then, of course, this I did after getting admitted to IIT Bombay for electrical engineering, and my father was extremely unhappy that I took up the National Science Talent Scholarship instead. Because in those days, the Science Talent Scholarship involved doing pure science. You couldn't get it if you did engineering. So my father was extremely unhappy. You got an electrical engineering and dropped it. Okay, so be it. Then I joined IIT again. I think that was in '74 after I did my BSc. And this time, of course, I actually went to classes for 2 weeks, but I had just for fun given the interview for BRC, and I didn't come to know much later, maybe 20 years later, that CVK Baba was on that committee. I didn't remember anything about that interview at all, and so I was selected for that, and then I had to decide, and basically it was a toss of a coin. Half the people I talked to said it's good to go, half said no, you should go after MSc, do a PhD, and whatnot. Anyway, I chose that, and I was lucky that I could get to the group of Professor CVK Baba in Van de Graaff Lab Nuclear Physics Division. So my first job, of course, for any experimentalist, the general thing is you work with your hands, make a power supply. So plus minus 12 volt power supply was what I first worked on. Then that was the first time I in fact held a soldering iron, because in colleges you don't get that opportunity to do things, at least not in those days in our college. So you learn how to use a multimeter, oscilloscope and things like that. And also, since it was a Van de Graaff lab, there was also this iron source where the glass was cleaned after its use using hydrofluoric acid. So we were taught how to handle things carefully, especially when you clean with hydrofluoric acid and so on. Anyway, so this is part of our run up to do experiment. But within a month, CVK said you come on a night shift. Some experiment was going on at Van de Graaff, and it was a gamma ray spectroscopy run of a gentleman called, it was work for his thesis, Dr. Bharati, SM Bharati, who actually passed away recently in IIT Bombay. He was a professor there, retired, he passed away recently. Okay. Anyway, so that's how things started. And so I made up these, I made these slides to show my gratitude and indeed, CVK Baba was my teacher. Of course, he was also my colleague, and he passed away in 2006. But we had interactions almost up to the end. He was a great person to learn from, and very open-minded, wide range of things that he knew fairly deeply. And anyway, so some of the pictures show him as well as some of the other members whom I have interacted with. For instance, in the middle picture you have Vandana, Raj Pillai and Naveen. And in the picture to the right, you see a much younger Murthy with a lot of hair. Okay, and of course Professor Narasimham, who was the who was the main person behind the proton decay experiment at the Kolar Goldfields. Yeah, that is Raj Pillai. Yeah, in the middle picture. Yeah. Okay, so before I start, let me also say something which I feel strongly about, and I think Indumati said that this is a good idea to have such a slide, and this is that an experimental nuclear physics background gives quite a bit of all-round training in many areas. I mean, you learn about vacuum pumps, you learn about cryogenics, you learn about electronics, how to get things going, how to use modules, and also importantly, when you at least compare it to the high energy physics these days, and also the high energy nuclear physics these days, the low energy nuclear physics provides you with the possibility of actually planning an experiment right from the start. What kind of detectors you should have, build them, assemble them if you don't have the possibility of making them yourself, carry out the experiment, analyze the data, because this doesn't require huge amount of computational resources and so on, and then actually write a paper. So it takes you through the whole gamut of activities that you do, and this is not there in many areas now of high energy physics, because the experiments are huge, they involve thousands of people, you are only a small cog in the wheel and so on. And so I think nuclear physics, low energy nuclear physics people are actually quite well trained from that point of view. They have worked with their hands. Okay. So with this I come to my early years in Van de Graaff. So this just shows some pictures. For instance, here you see Dr. Ramanna at the time of inauguration of the 5.5 million volt Van de Graaff in BRC talking to Bhabha. Couldn't find a picture of Van de Graaff. Unfortunately, we don't maintain records in BRC too much. So this is the picture of the upgraded machine. So it is from the same basic machine, 5.5 million volt, but another tube was put in so that it became, instead of a single-ended high voltage machine, a folded tandem. So you inject negative ions and so on. So anyway, this is the kind of size of the tank which houses the accelerating columns. This is a 6-cap orange spectrometer which was made by Baba and his colleagues, which allows you to actually measure low energy conversion electrons, and this complements gamma ray detectors in terms of taking data. So it can fix multipolarities very easily as compared to equivalent gamma ray measurements. Okay, so I'll list in 2 slides the kinds of things that I was involved in. So as I said, the first experiment that I was involved in within a month of joining was a spectroscopy experiment, which also used the 6-gap conversion electron spectrometer. It was to look for basically rotational bands in 72 chromium and shape coexistence. In other words, there are some nuclei where you don't have a definite shape, or at least at a low excitation you can go to some other shape, very different shape. So this is something that was done. This was part of, as I said, Dr. Bharti's thesis, PhD thesis. Then again, very quickly, we looked at some data which was already existing, so-called intermediate structure in PP prime E scattering, where again the electron spectrometer was used by Bettigiri, Baba and others. And a possible explanation of that was that Baba thought that this was perhaps due to a second well, and these intermediate structures were due to states in that second well. So they are fewer, but they mix with the background states, and that's how you get into it. So we actually look for a gamma ray transition between these resonant structures and ground state states. Of course, we didn't find it, but this was my first paper which I presented very proudly in the BAE symposium. And actually I remember this because Ramanna, I think, was great that way to encourage young people. So after the talk, he came and patted me on the back, and I felt great. I did a reasonably good job. Okay. So then we worked on, this is quite a unique case. This was pointed out by S.K. Bhattacharjee, the senior professor in TIFR. He found this in an article somewhere. It was actually some school, I think. A case which is quite unique because there's no other case in the NZ table, okay, as of now, where you can measure the difference in the mean field radii for protons and neutrons by looking at a particular branch of a beta decay. I'll come to that. There's one slide on this. We also, at that time, the machine was not working particularly well. It was towards the end of its life, the 5.5 MV machine. But we managed to do this, I think this was the second last experiment, to look for a color van der Waals force that might be mediated perhaps by some gluon states which have a combined color of zero, no color, colorless, and that led to a 1 by r to the power of n interaction between strong interaction. There was some indication, and anyway, I'll come to that also. There is a slide on that as well. Okay. We also searched for polyneutrons of the order of 6 to 8 neutrons, because there was an experiment which was reported from Fermilab, Turkevich et al., which said that they had found evidence for this in some very high energy proton spallation reaction. So we looked for it in the fission of 236, because in fission, of course, you know that lots of neutrons are emitted, and there is, if this state exists, there is a possibility of a bound polyneutron state. And the way we looked for it, because I don't have a slide on this, the way we looked for it is through it making a fusion reaction with lead 208 and then populating heavier leads and then looking for their decay. We could put pretty tight bounds on this process. An experiment that we couldn't figure out why it failed was this experiment at looking for convergent electron spectroscopy of neutron-rich fission fragments from spontaneous fission of californium-252. We tried all kinds of things. We had a plastic scintillator, very thin plastic, to measure the fission fragments. We put metal on top of that so that it doesn't get charged up by the fission fragments, what not. We tried lots of things. However, we failed to find a good convergent electron spectrum. I still cannot figure out why that happened, but anyway, it happened. And we spent quite a bit of time on that, I think something like 6 months, trying various things, but with no success. But this was something that sounded interesting when it was done. Actually, the source was not got for this purpose. It was got to measure some magnetic moment of a state in tellurium-132. But CVK was scooped in that, because that result, by the time this source came and so on, it was already done in Weizmann Institute. So then we had to find other uses for this, and this was one of the possibilities, but somehow it never worked out. Then we searched for the standard axion. Of course, this axion is still not found to this day, and people are looking for extremely ultralight axions. But at that time, the standard axion was believed to be something like 100 keV times 10 to the power of plus minus 1. Okay, so it could be between 10 keV and an MeV or something. So we looked for it first at Apsara to set up things right, because Apsara was just next door, and then we looked for it in the Tarapur power reactor. We also searched for electric charge non-conservation in beta decay, and I'll come to that. There is a slide on this. So we searched for the 17 keV neutrino, searched for high energy Bremsstrahlung emitted when fission fragments separate from in the spontaneous fission of californium-252. Yeah, okay, so I come to that. So as you can see, there are several experiments with null results. So it was natural later on to move to neutrino, the neutrino project. So we were used to having low counts, not finding anything, but of course in the neutrino case we would find something. So this is a natural extension later on. Okay, so I come to the first slide where we measured this difference between the mean field radii for neutrons and protons. As you know, neutrons and protons move in a mean field in a nucleus, which is created by themselves. And it is not absolutely clear, although there is a strong NP interaction, that these two radii be exactly the same. Indeed, for neutron-rich nuclei, we definitely know, very neutron-rich nuclei, that the neutron radius goes further out. Also, it depends on the binding energies of these. So as you put more and more neutrons, they become less and less bound, and of course the radius has to increase as a result. But for stable nuclei, most of the time this, can we attack this problem experimentally? Okay. So the way people do it is you measure the charge radius using electron scattering. Okay. You can indeed not just get the charge radius, you can get detailed charge distributions in the nucleus. And then you can get also matter distribution, nuclear matter distributions, that means N plus proton, through scattering of hadrons. And you can do that by scattering high energy protons, neutrons, pions, kaons and whatnot. Okay, in some cases actually if you are on the resonance, then pi plus may interact more with the protons, whereas if you are on the resonance for the pi minus prefers to interact more with the neutron and so on. So you can get these some handles on the differences as well. Now, if you want to talk about particular orbitals, then there is one classic case where electron scattering on lead-206 and thallium-205, which is different by just one proton, has been measured very precisely, and it gives specific information on that last proton orbital, the radial distribution. Now in this case, Lawson pointed out that if you look at this decay of the 209 thallium, which has a last 3s half proton, and that decays to lead 209 if you look for this state, it actually decays mainly to another state, which is the half minus state. But if you look for this specifically, then one of the terms in that matrix element will involve a radial overlap integral. And since these two are differing in n, okay, the overlap integral should be 0 if the radii are identical. Okay. So forget about all these constants, but the half-life is basically inversely dependent on this overlap integral, which is 0 if Rp is equal to Rn, and some small contributions due to two-particle, two-hole admixtures in the final state wave function. Now this was calculated by this gentleman who was a great nuclear theorist, Chindu Varke, and I just did the computation of that. He set up all that algebra involving 6j, 9j symbols and this and that, and I just computed it, and we found that this has a certain value, and if you put this in, we found that we actually get an upper bound on this branching ratio, 209 thallium to this half plus state is less than 1.1%. So this is actually our number, okay, this is our measurement. And if you put that in, then you can get this delta RPN, which is the difference in radii between the proton and neutron mean fields, the radius parameters. Then that difference divided by the mean radius is less than 2%. And that's a very nice result because this is done experimentally. You don't have to invoke any theory or not much of theory at least. Because this is a small number and that's what it is. And then this was corroborated when this was communicated by CVK to one of his friends, Negle in MIT. He said that yes, this is of the right order.
The shell model.
Pardon?
The shell model.
Yeah, this is computed in the shell model, yeah. The spherical shell model.
So this bound is within the shell.
Yeah. Okay, then I come to this 1 by Rn interaction. Okay, this is the setup. You have a beam of protons coming in, hitting a lead target, and you basically do just elastic scattering. Now you look at forward angles, so you have two detectors so that if the beam moves a little bit, if you take a geometric mean, it corrects to first order for this. But you minimize the effect of the beam wandering by actually putting a pair of slits here and putting a feedback so that if it moves to one slit more, you give a feedback. So there is a dipole magnet before this, which sorry, this is the slits and this is the magnet steerer. So then you bring it back to the center. Okay, so this is a control which we rigged up. And similarly, if it goes up or down, you can again give a feedback to the dipole so as to correct it. And if it goes up, you bring it down. If it goes down, you bring it up. So that way we could maintain the position on this of the order of a fraction of a millimeter. Okay, whereas the beam size is about 2 millimeters. So with that, then we looked at just forward angle scattering and looked at how constant these were, the ratio of this, and they were constant over a few hours at least. Now what happens is if you look at this geometric mean after doing all this, and you look at the backward angle scattering. Now the backward angle scattering basically comes from small impact parameters. Okay, in Coulomb scattering you know that, right? Small impact parameters give rise to a large scattering angle. Now when it comes close, it is more sensitive to a more sharply varying power law. So 1 by R7 for instance, that is what we are probing. Is much faster than 1 by R, right? The Coulomb potential. So, and it's also attractive, that's what we are looking for, as opposed to the Coulomb potential which is repulsive. So if you plot this backward to forward ratio, geometric mean of this divided by the geometric mean of this, with all this correction and so on, then you get a flat data point. This fits a flat line as a function of beam energy. As you increase the beam energy, you expect more of this effect to happen. Okay, when you are far away, this effect will be small and it will be 1 anyway. So just to see that this is just not an artifact, unknown artifact, we also repeated the measurement for the deuteron, and the deuteron indeed shows an effect, because in the case of a deuteron it is polarizable. Okay, once it is polarized, it also attracts. So it leads to a small effect of the order of about 0.3 or 0.4%, which we indeed see with the statistics we have. So we are sensitive. But in the case of the proton on this, because the proton dipole polarizability is very small, it is there, it is finite, but it's very tiny as compared to that of a deuteron, and so that effect is negligible. So you can put bounds on a possible 1 by R7 potential. Of course, indeed you can do that for 1 by R6, R5 and so on, and so in the paper such things are mentioned. So anyway, we could put some bound on a possible potential like this. Okay, then another experiment to look at charge non-conservation. Before I say anything, let me quote from Feinberg and Goldhaber in a 59 review article. The basic principles of theoretical physics cannot be accepted a priori, no matter how convincing they may seem, but rather must be justified on the basis of relevant experiments. Remember that it was just a couple of years after parity violation was discovered. So parity violation was a big shock to the whole community, because everybody believed that parity is conserved, and when it was found that it is violated and violated maximally, then it was a big shock, and that's how then people started looking for violations elsewhere too. And so electric charge conservation, this is, of course it depends on the the gauge invariance of the electromagnetic field, but nevertheless Goldhaber pointed out that any theory is only as good as it as it is tested up to. So this was the basis for, in fact they made the first search for electric charge non-conservation in beta decay. So as you can see, let's say a neutron decays to a proton, beta minus, and an anti-electron neutrino. This is the normal charge conserving beta decay. But you can also have in principle a decay which violates charge conservation. So you don't have this beta. So you just replace it by a neutrino, for example, among other things. Okay? And this would be the charge non-conserving decay. What would be the effect of this? The effect of this is that in cases where a decay to a state is not possible otherwise, because you get an advantage of this 511 keV, the rest mass of the electron, you can actually populate something through this charge non-conserving decay. Okay, so we looked for this 2.8 hour activity of strontium in kilogram or so of rubidium salt, separated out chemically, and then looked for this decay, which is a M4 decay, which means it mainly decays by conversion electrons, but you also need something else if you want to reduce the background to low enough levels. So we did this experiment in coincidence with the X-ray. So when you kick out a K electron, that hole has to be filled obviously, and you get a K X-ray. So you can do a K X-ray conversion electron coincidence measurement, and that way you reduce the background. But one interesting thing that we also saw, that this was not the only thing that was necessary to be done. We also had to remove noise from the main line, and so what we did is we put another detector with no silly in between, just two pairs of leads which could pick up any signal from the mains or radiative pickup and so on, and put that in anti-coincidence. That rate is of course not too high, so you could put a threshold and put it in anti-coincidence. That way then the noise completely went away. So this way we could put a bound on the charge non-conserving decay, and of course from time to time you calibrate this with standard sources and that, and so you could put a bound. This bound turned out to be about a factor of 40 better than the bound that existed at that time, due to the gentleman Norman in Berkeley. He had put this bound earlier, and we could improve it. However, much later, when the gallium experiment came online for looking at solar neutrinos, in particular also PP neutrinos, then of course they had tons of gallium, tens of tons actually, as compared to our kilograms, and so of course they could get a much better bound, in fact a 6 order of magnitude improvement. And so this is the current status. And then there is also another neutrino experiment which has contributed to putting a bound on electron charge non-conserving decay of about an order of magnitude poorer bound. Of course all of us believe that electric charge is conserved, but who knows. Okay, then there is a search for a light mass axion in thermal capture. This was necessitated by a paper by Pechai Quinn, and later a couple of papers by Weinberg and Wilczek, who said that there should be a light axion, and if this symmetry restoration that is involved in this takes place at electroweak energies, then this axion could have masses of the order of 100 keV. Again, as I said, give or take a factor of 10. And if this particle exists, then it would, if it is less than 1 MeV, then of course it would decay by 2 photons. If it is more than 1 MeV, which is the sum of the masses of the electron and positron, then it would decay by electron and positrons. Indeed, in one of the experiments, Indumati was involved in Van de Graaff, which looked at a transition, a nuclear transition which decays to, which is I think greater than 1 MeV transition. I also looked for it in in some other transition. Okay, but the first one that we looked at was this, and this was due to a gentleman called Nimai Mukhopadhyay. He used to come every year to Mumbai. He was, I think before that he was a graduate student also in TIFR. So he came very excited saying that, a reactor, a nuclear reactor, especially the light water ones, they could be, prolific sources of axions. So why don't you look for them? And since they involved light water, of course you had to go to a light water moderated reactor, and that happens to be this Tarapur reactor. So there is also a light water reactor in Mumbai, in BRC. So we first looked at it at Apsara. That was a very low wattage, 400 kilowatt thermal. Then we looked for it at, so we set up something there and we got a hang for what to do. Then we went with better detectors. So we had done this with sodium iodide, which are poor resolution detectors. We did this experiment in Tarapur using germanium detectors, which are very high resolution. And the way we looked at it was that just outside the biological shield, we put a big lead shield and then looked for a possible axion which would decay into 2 photons. So we kept these 2 germanium detectors shielded from each other, so they would, you would not get scattering from one detector to the other as far as possible. And then we ran this experiment, and fortunately or unfortunately there was a lot of cobalt-60 activity on the floor of the reactor, but that provided an internal calibration, because then that provided a cascade of gamma rays, 1.17 and 1.33, which went into these 2 separate detectors. So if you see no signal, you always are worried whether your things are going right or wrong. I mean, you don't see anything, but maybe something is not working. But in this case, there was a background, internal background, so we could see the sum peak, and indeed we saw no peak at the binding energy, because the NP reaction normally goes through a D gamma, capture gamma ray, M1 photon. But it could also go into an axion if this existed, at least the standard axion, and then that would decay further. So these 2 photons, some energy would be the binding energy of the deuteron, which is about 2.2 MeV, and we looked for that, didn't find it, and this experiment alone was not enough to rule out the axion. There was another experiment which was taking place in Zurich, I think, which was looking at a transition in cesium, or following the beta decay of cesium-137, which is a standard gamma ray calibration source, and that looked at basically the isoscalar coupling of the axion to the nucleus, whereas this had both components, isoscalar as well as isovector. So combining these 2 experiments, we could rule out the standard axion. So okay, in each case I give the reference here. If the authors are too many, then of course I just say et al. In this case, there are not too many authors.
Question.
Yeah, sorry.
Is axion part of standard model, or it's beyond standard?
Well, I mean, the way it comes about is that there is something called the Theta Anomaly. You know probably better, or the high energy guys know it better. So the QCD Lagrangian is respects CPT and so on, but this instanton solution apparently violates that, and so you get some component added to the QCD Lagrangian which violates parity and time reversal invariance. So if CPT is conserved, then it violates CP. Okay, so you have to do something in order to cancel that, and so then you require a Goldstone boson of a spontaneously broken symmetry, and that's how the axion appears. It's a Goldstone boson in that sense. Okay. So anyway, so this is another of those zero null result experiments I talked about. This is another null result experiment. So there is, as Murthy has already said, Simpson found a 3% mixing in the beta decay of tritium, and tritium has an endpoint of about 18.6 keV. So with the 17 keV, you expect, then he saw a bump ending at about 1.6 keV. Now that's pretty low, but he was pretty sure of his detector response and so on. He had implanted tritium into this silly detector, and he claimed that he knew its response perfectly, and so this was a 3% mixing that he found. Of course, if there is 3% mixing, then you expect it in all other beta decays as well. But you don't want to go too high Q value beta decays, because then it will be difficult to get enough counts there. So it turned out, and also that if it is accessible easily, that makes it all the more better. So we found quickly that sulfur 35 is something that you can make in Cyrus reactor. At that time we had Cyrus running, and so we irradiated a salt, a chloride of some, I don't remember, I think it was sodium chloride or potassium chloride or something, and then the radiochemist in TFR extracted sulfur from there, made a thin beta source, and we put it in the same, just in front of the same detector that we had used for electric charge non-conservation measurements. And in about 2 weeks' time, we had enough data to show that you don't have mixing more than 0.6%. So that contradicts Simpson. And of course, subsequently, there were many other experiments that pushed this bound another factor of 10 or so. using also very fancy magnetic spectrometers and so on. This was done very quickly, and that's how, although we were advised by Professor Bhattacharya, who was more of a conservative person, that we should just give this manuscript to physical review, not even physical review letters. This Prabir Roy met him once and said, yeah, I'm hearing that you're putting it to physical review. No, this is put it in Nature. So anyway, it went to Nature, and surprisingly, but not so surprisingly probably, because it was a current topic, and that's why they accepted it without any change at all. I mean, they just accepted it. Okay. So anyway, we put a bound on the, and the reason why we couldn't put a slightly better bound, maybe we would have improved this by a factor of 2 by counting it for maybe a couple of months. But then of course the graduate student comes in, his role comes in, he let in air into a cooled, liquid nitrogen cooled detector and put all moisture all over the place. I mean, he didn't do it intentionally, of course, did it by mistake. But anyway, that's how we got a 0.6, otherwise perhaps we could got a 0.4% limit or something. Okay, now a small excursion into atomic physics. CVK had this, he saw this paper in the library. He said that, oh, there is some paper which claims that there is a transition in beamfoil spectroscopy. Somehow we had got interested in beamfoil spectroscopy. The low energy machine coming up at that time, Bettigary was making it. And so he said, oh, there is a transition which these guys are saying that maybe this is a transition in a negative ion, an excited state of a negative ion. Now, of course, you know that negative ions have very few excited states, if at all. Even if there is a negative ion in the ground state, you can attach an electron with some binding energy. But if you put one more electron, it's very hard to make it bound in an excited state. Sorry, one more electron, that is very tough. Similarly, if you excite this guy, also it is very tough to have a bound state. Okay, so generally negative ions have either no excited state, no particle bound state, or maybe they have one or maximum 2 perhaps.
Hydrogen supports a negative ion.
Pardon?
Hydrogen.
Yeah, so I'll come to that, by the way, I'll come to that. Yeah. So there's a transition, which was this 3489 transition, which was supposed to, which could have been this negative ion transition. But how do you show it experimentally? So he had a very nice idea. You just, so you excite this through beamfoil spectroscopy. So you shoot a lithium beam onto a carbon, very thin carbon foil. As it comes out, you get all kinds of excited states, core excited states, multiply excited states, and so on. And so this state will also be produced. Of course, you have to be low energy. If you go to too high in energy, then of course all the electrons will get stripped off, sequentially. So, and then if you have an electric field here, then the negative ion will move one way and the positive ion will move the other way, the neutron guy will go straight. So this is very simple. So we built this apparatus. We fortunately had a machine in TIFR. Kuru Sharma were managing this machine in the mezzanine floor there, 400 kilovolt machine, and we saw these transitions in a spectrometer from the atomic physics division in BRC, and of course we measured the lifetime. That was just a byproduct. But we basically showed that the lithium ions, the negative ions, this line, the emitter actually moves one way or the other depending on the direction of the field. And if you have a transition in a neutral atom, then of course whatever field you put doesn't matter. There is a neutral atom, it doesn't get affected, and that stays put. So you can see with 20 plus minus 20 kilovolt, it just stays there. Whereas in this case, it moves in opposite directions. And indeed, I didn't show it here because it would clutter up the slide, but believe me, it's there in the paper, that the positive ion transition shows exactly the opposite behavior as the negative ion. So it's very clear cut. It showed that this transition is coming from. So inspired by this, I went ahead and tried to search for the similar state in hydrogen minus. So this state has been predicted in 1960, and in 1970 there was a much better calculation by one of the leaders in this field, GWF Drake, and he himself actually tried to look for this state by colliding cross collided beam target experiment, where mercury vapor was going one way, was effusing one way, and then this proton beam comes, and then he looked for this transition. He didn't find it. We looked for it in the beamfoil spectroscopy way, except that this time we were looking for the photons in coincidence with the electrons. So I made the the electrostatic analyzer for the electrons, checked it out with a filament, and unfortunately we were unsuccessful. This was an experiment that was done just before the pelletron came online, so we had time. And we found that it is less than 10 to the minus 4 of the delta electron. Delta electrons are the electrons that go with the same velocity as the proton beam. So, okay, so then I thought that we should do a better experiment with a better detector for photons, with a filter so that no electrons can reach the photon detector and so on. So this got built actually by a very good student from CBS, Kalina. This is this DAE Institute for undergrad teaching, and he did a very good job. He learned CAD, he made a drawing, he got it done in the workshop. Unfortunately, they have only 6 months, and in that 6 months we could not get beam time at Van de Graaff. There was a small accelerator there, but we couldn't. So anyway, but this problem is still in my mind. I hope that if I can get somebody excited, this can be done, because this is a very simple system. The only catch with this is that this is at this has a binding energy of only 9.5 milli electron volts. So it is quite possible that a beamfoil spectroscopy measurement you may not see it. That's quite possible, because there are also fields that it will see as it comes out of the foil. First of all, the simplest is that as the negative ion comes out, it sees a mirror image of it on this conductor on the other side, and that produces an electric field, and so you can stark ionize this stuff even if it is produced. But let's see. This is one way. The other way is once we get a gas jet target, then I think there is another approach to this problem. And also I was happy that there is a proposal to look at this in a very different way in Fermilab, where they have a relativistic beam. Oh, this is not getting stuck. So there is a relativistic beam of protons, and you can shoot a visible wavelength laser on it, and because it's relativistic, it gets Doppler shifted. And then you can have, because it's a laser, it has a high intensity of photons, you can have 2 photon absorption. So from the 1s2 ground state of H minus, you can go to the 2p2 state, which this is, right? This is the 2p2 state. So that was, but I think that experiment never got done. It was a very nice proposal, but it never got done. So there is still an opportunity in low energy, setups that we can try to look at this. I think this is a very nice case, a very simple case, but it has not been measured experimentally. Okay. Then I come to experiments at the VRC-TFR so-called Pelletron LINAC facility. This has been running since '88, so now it's what, 12 plus 22, over 40 years now. So it basically is a 14 million volt tandem accelerator. So you inject negative ions, they get accelerated by the electric field here. Then there is a stripper which removes some or all electrons depending on its atomic number and velocity. And then you accelerate this, because now there are positive ions, the terminal is at a positive voltage, that's what attracts these negative ions, and then these get further accelerated, and then you can analyze them using a so-called analyzing magnet. And this was the old Cascade Hall where we had set up experiments. Later on, this superconducting LINAC booster came up, which roughly doubled this energy. So this is a LINAC which is made using superconducting cavities of copper plated with lead and so on, and they roughly double the energy. And so I'll come to that. They go to a different set of beam halls. Okay, so these are some pictures from there. This is one of the cavities. There is a central conductor, and then these are at ground essentially. So the ion gets accelerated here and here. By the time it comes here, the RF phase has flipped. And then there are 4 such cavities in one box. And then this is again some pictures of the top of this cryostat. These are some of the racks which have the RF electronics, because you need control of the RF both in terms of amplitude as well as in terms of phase. And similarly, this is another picture of the beamline. One is the incoming, the 3 or 4 cavities in the incoming side, then the bend and the further cavities. And so the key members here were of course Raj Pillai and Kurup. Kurup has passed away. Then other key members, younger members, Srinivasan, of course now Vandana is managing the whole business there. So this is one of the beam halls, LINAC beam hall. There are 3 beam lines, 15, 30 and 45 degrees. We used to work here. You can see some apparatus here, high energy gamma ray detector, BGO multiplicity array, so as to get a tag on the angular momentum that is populated in a heavy ion fusion reaction. And then this is LINAC beam hall 2, where in one of the beam lines there was a this was an early picture. There is a so-called INGA setup, high resolution germanium detector array, for looking at high spin states in nuclei. These are some of the other things that are there. this is the setup, high energy gamma ray setup. This can, you have an array of closely packed barium fluoride hexagonal cross section detectors and this multiplicity array. This is a this was again in some detail 38 VGO multiplicity array. This is a neutron time of flight array consisting of plastic scintillators viewed by 2 photomultipliers at either end. So it's 1 meter long and about 6 centimeters on the side, square cross section, and then there are about 15 of them here. Similarly, this is a INGA in an early implementation of it, 2006, where there were I think 8 of these detectors. You can see 4 and 4, 8, yeah. And then you don't want to detect very low energy gamma rays in this, so you put we had a ledge wall in front of it, again found from the scrap in BRC. We had many things that we found in scrap or in somebody's cupboard, and we used to regularly take advantage of that. Okay, so I'll discuss some, let me see how am I doing in time. Yeah, okay. So I might exceed it by a little bit, I hope you don't mind. So I'll talk about giant dipole resonance in, built on high excitation and angular momentum states in nuclei, the energy dependence of the nuclear level density, the melting of shell effects as seen through the nuclear level density in doubly closed shell lead nuclei, and radiative transitions in 8 beryllium, which is, you know, you might say is equivalent of a hydrogen molecule. Okay, there's a 2 alpha cluster. Okay, so just to give you a background, nuclear collisions start of course from high impact parameter, which leads to elastic scattering, to slightly smaller impact parameters, which leads to Coulomb excitation, then to pickup and stripping reaction, inelastic scattering could be of both projectile as well as target, and deep inelastic, where you lose a lot of energy in a collision, and finally if the impact parameter is small enough that there is enough overlap, then you get fusion reactions, which ultimately leads to a compound nucleus. This is what happens at low energies, of course. This is typically up to 5 to maybe 7 MeV per nucleon, okay, just a little above the Coulomb barrier. When it comes to models and trying to understand the nucleus, of course, we still are I think a long way from understanding it really like, you know, you can understand the hydrogen atom, for instance. You can do this calculation, you know, to any order that you want. It just takes more time, more computation. Because the nucleus is much more complicated. The interaction is the main reason why it's complicated, but also because it's a compact system of these strongly interacting. So it's a many body system, but also because the interaction itself is complicated. So you have these many models. Geometric models, deformed shell model, then shell model, cluster model, and ab initio calculations, which have now I think proceeded a little beyond A equal to 12. I think maybe they have gone up to A equal to 16. There are of course approximations which can do it right up to A equal to 250 and so on. But those I wouldn't term them as really ab initio. Ab initio ones are still hovering around A16 and so on. And then there is the experimentalist who is looking at various things and who is trying to understand what
Sorry, what about liquid drop model?
Yeah. Sorry?
Famous liquid drop model. Is that cluster model? Droplet model?
No. This is cluster, I mean, in terms of, I think the best cluster is the alpha cluster. So they are in light nuclei and, things like lithium 6, lithium 7. You can talk of the nucleus in terms of alpha D or alpha T cluster. Similarly, in beryllium 8, you can talk of it as 2 alpha clusters. Beryllium 9 has 2 alpha clusters and a neutron. But you can't take this to very heavy nuclei. By the time you get to heavy nuclei, this cluster structure then disappears. Of course, some of it remains on the surface. Where there is low density, this alpha clusters still hang around. And that's how, in fact, this is an interpretation of alpha, spontaneous alpha decay. They are hovering around, once in a way they pierce, they tunnel through. And that's how you get alpha decay. Okay. So now this slide, I beg forgiveness for this. The slide is a bit busy, but don't worry about all that is written here. We were trying to look for so-called giant dipole resonance, which is a very generic thing in all parts of the periodic table. You have basically protons and neutrons oscillating against each other. Okay, that's the so-called giant dipole resonance. It has an angular momentum of 1 embedded in it, and it can be seen through gamma ray transitions. Okay, so they are high energy. Typically, the energies involved are of the order of 80 by A to the 1/3. A to the 1/3 reminds you of the nuclear radius. So indeed, they go like 1 by R of the radius of the nucleus. So the heavier the nucleus, the lower is the resonance energy. Now, in studying this, I think the analogy would be that you beat a drum, you get its resonant frequencies, the frequencies that it emits, and you try to figure out what the drum looks like. So in this case, you get these giant dipole gamma rays, and you are trying to figure out the shape of nuclei and how these giant dipole gamma rays acquire their width, how they mix with background states and so on, whether they exhaust the total sum rule. Indeed, the way this giant dipole resonance was seen in the early 40s was that you photo excite it, and you see this photo excitation across the board, and you see a large bump, and that was attributed to this giant dipole resonance. This is, by the way, also there in atoms, so-called plasmon resonances and so on. Okay, so you can infer about the shapes of these nuclei in excited states. So now Brink showed some time ago that on every intrinsic state of the nucleus, there is a single particle state, you can have a giant dipole resonance. Okay, so you can actually have any, now this can be generalized, any excited state can have a giant dipole, because what is the giant dipole in microscopic term? It is a coherent one particle one hole excitation, and that can be there on any state. So this state is something that can be studied, and we studied it on these excited states in nuclei. At that time when we started these studies, nobody had done exclusive measurements, so we did these measurements in coincidence with a multiplicity array. So you can get some idea of how this giant dipole strength evolves as a function of angular momentum. So anyway, these are some examples of that. I think I will not dwell too much on this, except that we extract, we did this for many energies, and then at one energy we did a higher statistics experiment to get data on various folds, and then try to see what is the behavior with it. So we conclude that there are shape fluctuations which are needed to understand this broadened E1 strength function, and also some triaxiality. But I would say that these are details. Another experiment that we did was to look at the so-called Jacobi transition in a light nucleus populated by this reaction. So this is, I think, 46 titanium, if I'm not mistaken, or vanadium, I forget. This is 9 and this is 13, so 22, Z equal to 22, whatever that nucleus is. So in the liquid drop regime, indeed in any classical system, if you keep spinning something faster and faster, even a gravitational system, like the Earth for instance, as you spin a body, it becomes oblate, right? It becomes less north to south and as compared to east-west. So this does happen even in nuclei, because nuclei also are reasonably, the broad understanding of that is still reasonable in terms of the liquid drop model. Now when this, except that this is a charged liquid drop model, so there is also repulsion, internal repulsion. So as you spin it up, it does become oblate, but at some point there is a transition to a triaxial and more prolate shape before it breaks up. Okay. So this is something that is predicted in nuclei using a macroscopic approach, so-called Strutinsky approach. And in light nuclei this happens at relatively low critical angular momenta. Heavy nuclei it happens at very high angular momenta, where then fission starts competing. Here fortunately fission is not such a big competitor. So we chose to look at this in light nuclei, and there was an experiment done in VECC which saw evidence for this, but that was an inclusive experiment, so we decided to do an exclusive experiment. So we measured the gamma rays in coincidence with the multiplicity array, so you know that this happens at high angular momentum, and also we did measure the fusion residues through a gas detector called a parallel plate avalanche counter, so that you cut down the background coming from other reaction mechanisms. We did this at 2 energies. And so the point here is that we extracted a photo absorption cross section from this data. You can see that this is done at 125 MeV and this is done at, this is I think inclusive data. But what is shown here is that this inclusive data has a mild bump here which disappears when you do in coincidence with the p-pack. So when you gate on the residues, evaporation residues, that goes away. So it cleans up the data. So you are more confident of what you extract. And what is extracted in the higher energy data which populates the high angular momentum, you see a relatively narrow component at very low energies, which corresponds to a very largely prolate shape, because then there are 2 short axes, and a short axis gives you a high energy, a long axis gives you a small energy. So this corresponds to the long axis. But that's only one component, and the other 2, so there's a weightage of 1:2 for the long axis to short axis in a prolate nucleus. So this is the component that you see, and so we conclude that we have evidence for supporting the VECC measurement, but with a much more exclusive measurement. So anyway, we confirmed the earlier evidence for the Jacobi transition at this particular angular momentum. We also did this for GDR on a specific excited state where the strength function looks very different from the strength function for photoabsorption on the ground state. But I think I am running a bit short of time, so I will quickly go through this. Okay, so we also we have a set of experiments on nuclear level densities by measuring particles. Now you know that the nuclear level density, which is just the number of levels of a given at a given excitation energy, given angular momentum, parity, isospin, and maybe other quantum numbers if you want, per unit energy interval. And this is a very fundamental quantity which is important when you calculate the statistical particle emission from an excited compound nucleus. And this was calculated indeed by Bethe in 1936, and interestingly using the Ramanujan-Hardy partition formula. Now the NLD, the way it is measured is in a very narrow region of excitation. You can actually count the neutron resonances, okay, thermal neutron resonances. You can count them. Of course, these are only S and P wave resonances because they are thermal neutrons. You don't have to bring in too much of angular momentum. When you are talking about the total level density, you need to integrate over all J possible. And as you go up in excitation energy, more J's are possible. So, but nevertheless, this is a experiment resonance measurement which can actually count these levels. And then you extrapolate using some theoretical formulation to the total nuclear level density. You can also do this in terms of fluctuation that you see in excitation functions and so on. Another method which was thought up by Chakravarti is that you can use high energy particle spectra and the energy dependence to extract the excitation energy dependence reverse. You can go back to the excitation energy dependence of the nuclear level density if you can populate this through heavy ion fusion reactions. And you can look at neutrons, protons. Alphas are composite particles, so interpretation may be a little more complicated. But nevertheless, if you look at neutrons and protons, you certainly can do something, and you can corroborate that with the alpha particle spectra. So we did a series of experiments, singles and exclusive coincidence measurements on this. Just to give you a flavor of this, the nuclear level density Exj, depending on Ex and J, goes roughly like, there is a factor which depends on J, it goes like roughly 2J plus 1, and an exponential square root of 2A small a times U. U is just the, okay, this is a slightly complicated, but in simple terms it is just excitation energy minus the rotational energy of a nucleus minus the pairing energy. Okay. So, and then this is the level density parameter. It goes like roughly like A by 8 in terms of a liquid drop picture, but it could be more complicated in closed shell nuclei and so on. And then if there is if you are close to a shell, then there is something called the shell correction. I will come to that. Okay, so I think that is there in the next slide. Okay, so the way we measure it is you measure these particle spectra using particle detectors, delta EE detectors, silicon detectors, or you can do that even with scintillator detectors, which show this property of pulse shape discrimination. That means the pulse from a proton looks slightly different. It has a slightly different decay time from the pulse originating from a gamma ray or from an alpha particle. And so you can distinguish. So if you plot a pulse shape parameter, which turns out actually crossover time, or you can take ratio of the charges in different time windows, you can make a pulse shape parameter as a function of energy deposited in the detector. You can see gammas, protons, deuterons, alphas are separated out. Of course, these things becomes closer when you go to heavier ions, but at least protons you can separate very cleanly using this sodium iodide detector. So that is exactly what we use, because you need a reasonable thickness to stop the high energy protons. Okay, so we did this, we made measurements initially in singles, and in singles measurements at various energies you just see a featureless exponentially dropping spectrum. Okay. Now the interesting thing is, when we started doing this coincidence measurement with the multiplicity in order to get the J dependence, then we found that when you put cuts on high J's, means high fold, how many detectors fire in coincidence, then you find structures start appearing. Okay, so look at this structure for instance. That means 5 of these multiplicity detectors out of 14 are firing. 6 of them are firing. And the bump in fact becomes more and more prominent as you go to higher and higher fold. Okay, now is this real or is this fake? Is this some artifact? So this is what we set out to investigate, and we did a series of experiments. We looked at different entrance channels. So instead of 12 carbon plus niobium, which is mentioned probably somewhere, 12 carbon plus niobium, we did 16 oxygen plus 89 yttrium, which populates the same compound nuclear state, and we again see the same bump. because of the larger Z, you have to go to a slightly higher energy, so this effect is not as strong as here, but nevertheless you see the bump even here. Then we did, said okay, maybe there is some other impurity that is contributing, so we did a evaporation residue high resolution detector gated spectrum, and of course the statistics reduces, but you still see the bump at high folds. So it's real, it's not just an artifact. And it is high multiplicity, that means it can't come from some light impurity. And finally, is it a massive transfer? That means is carbon coming, transferring beryllium, boron 11, and a proton goes away. Maybe it comes at back angles if you are at low energies. Sub-Coulomb things, transfer reactions also peak at back angles. Is that happening? No, because then there should be forward-backward asymmetry. Compound nuclear processes show forward-backward symmetry. Okay, there should be a symmetric thing about 90 degrees in the center of mass. Well, this is a light ion, so it doesn't make much difference even in the lab. But anyway, we showed that the backward-forward symmetry is there to within the errors of our measurement, and so we concluded that this is a real effect. Now, the explanation for that, one can't vouch for that with great certainty, but the likelihood is that this is coming about because of so-called pairing re-entrance in nuclei, where once you start spinning the nucleus, the pairing effect drops, it goes away, but then it can appear again at higher J because some other orbitals are involved, single particle states are involved. And the analog of this actually happens in condensed matter, where if you increase the magnetic field, I am told, I haven't looked up any reference, but I think Bhaskaran will know. If you increase the magnetic field, superconductivity goes away at some critical field, but it reappears in some cases, and that's called the re-entrant effect. And similar thing may be happening here, and this indeed gives rise to such a bump. And this has been calculated by Dean and colleagues in some other nucleus, but we think that a similar thing is happening here. Okay, so then we did this melting of shells, this in the same line, but this time not detecting protons but detecting neutrons using that large neutron time of flight array. So this detector is typically kept at about 1 meter from the target, and you see a time of flight spectrum, and we did this for 2 targets, one with closed shell where you address a closed shell nucleus, one away from the closed shell, and we find that there is a shell effect in the case of a nucleus close to lead-208 and no shell effect in the case of a nucleus away from that. So we did this measurement with thallium nucleus and with tantalum nucleus. And we also used a novel triton transfer fusion reaction. I call this the poor man's triton beam. Triton beams are difficult to get because it's a radioactive nucleus. So there are just 1 or 2 labs in the world where you have a triton beam. But using this transfer reaction, which involves only stable beams, you can get to the same states that you want to. And this effect was actually, the damping of the shell effect through the level density window was actually predicted by our own colleagues, senior colleagues, Ramurthy, Kapoor and Kataria way back in 70. And we showed, I think we have the first experimental evidence, and also a plot, a 2-dimensional exclusion plot of the parameters that are involved, the damping parameter, at what energies that this shell effect gets washed away, and the level density parameter. This is connected to that. Anyway, then I come to the rotating dumbbell. Beryllium 8 is one of those cases where you have 2 alphas, cluster coming together, and beryllium 8 is of course unbound in its ground state, but it has a very low positive energy of about 92 kilo electron volts. So it survives for a time scale much longer than the strong interaction time scale, which is about 10 to the minus 16 seconds. And that's fortunate because that's how then carbon can be made in the interior of stars. If it didn't live long enough, if that energy was about 100 kV more, then probably we wouldn't have had life on Earth as we know, or indeed anywhere else when we find it. So this particular nucleus exhibits a very nice rotational band, except that rare earth nuclei exhibits bands up to about 50, 60 H cross, whereas this one, by the time you get to 4 H cross, it's already at a very high excitation energy. So these are not narrow states, but they are resonances. Okay? So we looked at, so this is the picture of the level scheme. Beryllium 8 in its ground state actually decays to 2 alphas with a lifetime of about, this is given here in terms of electron volts, 6.8 electron volts, so that's about 10 to the minus 16 of a second. Then the 2 plus state is at about 3 MeV with a width, already a very large width in MeVs now, not in electron volts, 1.5 MeV, and the 4 plus state. We chose to look for this because that's easier experimentally to address. This branching ratio, gamma to alpha, is of the order of 10 to the minus 7. Okay? Whereas this branching ratio is a few times 10 to the minus 9. So this would be very difficult to measure. This is something that we hope to measure. And indeed we found in a coincidence experiment where you shoot alphas on a gas target and look at the gamma rays with a 38 BGO cluster, 19 plus 19 on top and bottom, and then you shield, since it's a gas target, you have to have Kapton windows which can withstand the radiation damage, and those lead to background of 4.4 MeV from the carbon in the Kapton, is organic compound. So they have to be shielded, so there's a heavy met shield so called. And then we detect the particles, the alpha particles in a silicon detector array, and that's shown here. So you have readouts of theta and phi on the opposite sides. So you can tell where one particle came, where the other particle came. And the idea is that when you shoot an alpha beam on a gas target, if this decays radiatively, normally you know that billiard ball on billiard ball, they scatter at 90 degrees in the lab, right? Whereas in this case, because they emit some gamma ray which carries away some energy, in this case about 8 MeV energy, the folding angle decreases from 90 to about 60 degrees. So you can use that as a handle to emphasize those type of events. And we did that, and then this is the region where you see these evidence for the radiative branch. This is the 3 points that we could get. We could only get a bound at the highest energy. And these ab initio calculations were also fortunately done by the old group of Pandri Pandey. Pandri Pandey actually started these kind of calculations. Of course, he wasn't there when the calculation for this particular case was done. So Viringa was the one who actually did this. He is part of this author list, and also his colleague. And interestingly, it's a good thing they don't quite agree. They overestimate the experimental result by about 30%. But this could be because of two reasons. We have made a very crude estimate of the BE2 by just assuming a bright Wigner. Now that can be improved perhaps, but it doesn't take into account the fact that there is a reaction also happening at the same time. So structure and reaction actually have to go together in a single theory. Usually in nuclear physics what happens is there are structure guys and there are reaction guys, and the twain don't meet. Okay. So this I think may also be the reason for this 30% overestimate. So hopefully this will excite some nuclear theorists one day and address this question. The future is that this transition in one model is enhanced by about 3 times more than the 4 to 2 plus transition in the cluster model, and 2 or 3 times I would say, and in the ab initio model it is roughly the same BE2. So you can very clearly distinguish it by doing an experiment. However, this requires a gas jet target, and so there are groups, 2 or 3 groups working on this, and when that happens then we will be able to do this experiment. Not only that, and another interesting thing that can be done with a gas target is that you could do an intrastate transition. That means you are on one edge of this resonance and you look for a transition to the other edge of this resonance, and then you can detect the alphas the same way. But this has to be done with a gas jet target. You can't do it without that. And this would be a very interesting thing. It would give you something which is the equivalent of a static E2 deformation in that excited state, which lives only for 10 to the minus 23 seconds or something. There is no other way you can measure it. Okay, so this would be a unique measurement in some sense. Okay, so now I come to another kind. I have already exceeded time, but I would like to say this. We are also involved in a measurement of astrophysical interest, namely the S17 measurement, the S factor for proton and beryllium 7. And this involved using the first RIB in India. J.J. Das is the one who is responsible for that. He made an extremely pure, 99.9% pure beam, just like you get from the Pelletron, 3 millimeter in size, delta theta of 1 degree and so on. And then we used the recoil mass. So the recoil mass separator was used to actually get this beryllium 7 beam. And the experiment was done at the focal plane of this. So this detector assembly was actually built by J.J. Das and his group, and we measured elastic scattering, the transfer reaction, beryllium 7 with a deuterated polyethylene target. So beryllium 7 plus deuteron going to N plus boron 8. That's the experiment we did. And then this is an indirect way that you can connect this up to the P gamma cross section. And also there are some niceties about extracting the systematic error by doing multiple calculations with optical model parameters that have to be used to interpret this transfer data. And so we have a systematic error, and basically we show that this earlier there was some tension between an indirect measurement of this sort, DN measurement by a Chinese group, and the direct measurements, which are these black dots, so these dots. So there was a big difference, almost by 50%, and we were able to show that no, this indirect measurement also agrees with the direct measurements. But more importantly, such a measurement can be used with radioactive beams to get S factors, through an indirect method, to a precision of about 10%. And since there is a strong interaction that is involved here, this has much more cross section than a radiative capture cross section. Radiative capture cross section at very low energies have cross sections of the order of picobarns. This has of the order of tens of millibarn cross section at 0 degrees. So this is much more easy to do, but you get a rough and quick result, and then you can build on that at some underground lab or radioactive ion beam lab and so on. Okay. Towards an underground lab, so anyway, I'll go quickly through this. I think such pictures would have been shown by Indumati sometime or the other. We built magnets at VECC, the 35-ton prototype. This is in connection with looking for atmospheric neutrinos eventually with a 51 kiloton detector for magnetized 51 kiloton detector called ICAL, iron calorimeter, for atmospheric neutrinos. So we did some first steps in that direction in 2008, 2010. 2018 we built a so-called mini ICAL detector, which is about 2.5 times this, and made measurements of cosmic muons and so on. And then we hope to build the engineering module, which is about 10 times bigger at VECC now. The place is decided. Hopefully it will come up in the next couple of years, and then eventually we'll build this at a location which I will come to maybe. So we have to do lots of R&D. So this is done by a large group of people in TIFR, led by Dr. Satyanarayana, and also another team that looked at other things like gas systems. So it involves making so-called glass resistive plate chambers in a company with special purpose machines, a gas system to put in and out the gas and recirculate it, then electronics. So these first hybrid chips were used. Then DAQ cards were made in-house, high voltage DC to DC cards were made in BRC, the front end board was made initially in TIFR, but then later also in BRC using an ASIC, which was designed by the BRC group, and of course trigger and calibration systems by the BRC TIFR group. Lots of things were done, and also lots of involvement of students. So both the INO graduate training program students, but also students from all over India, mainly I think also from Tamil Nadu, university and engineering students who have come at various times. And this detector, we did some calculations as part of a PhD thesis to look possibly for anomalous events seen at KGF. This detector being much bigger can be much more sensitive to that. And then we can also use this to search for magnetic monopoles, and you can get bounds which are better by about a factor of 5 or so compared to the best bound that exists for cosmic magnetic monopoles, and in about 5 years' time. Another idea that we examined was the possibility of using a cosmic muon veto detector to look at this possibility of a shallow detector. Now, even if that may not happen, because we think we have a deep underground site, but you could actually build this, at least a partial veto detector, to reduce your background, to almost make it background free. So cosmic muons which would give a background to neutrino detectors, you could reduce that background to almost zero. So this is some, okay, this I will not talk about right now, because we did a simulation to show that at shallow depth also it can work like a 1 kilometer depth, but it may not be needed, of course, when you go to a deep place, but it might add to the value of this by reducing the whatever little background there is to almost zero. Okay. Yeah, you could also use it for other things like magnetic monopoles, dark matter decays, because you have a big detector. Okay, again this I don't think I have the time, I think, or no time. Okay, so I'll quickly, just very quickly go through this. This is an idea that was born out of possibly looking at supernova neutrinos using a heavy water based scintillator detector. You all know that this 1 kiloton of deuterated heavy water, which has basically deuterium substituting hydrogen, was used very successfully by the Sudbury Neutrino Observatory group to actually solve the solar neutrino problem. Of course, this has, and in fact, it led to half a Nobel Prize for one of the proponents. Now, this has a high threshold because it depends on Cherenkov light of about 5 MeV. If you have a liquid scintillator, you have a 50 times bigger signal, so you can lower this threshold to 100 keV. Now, this of course means that you can, apart from supernova neutrino, you can also look at solar neutrinos in a very accurate way. And the advantage is that DAE has this possibility because heavy water board makes a lot of heavy water for its own nuclear reactor program. And so we are at an advantage. There was a statement once by Srinivas Kulkarni from Caltech. He comes to TFR. He says, you should not do an experiment unless you have an unnatural advantage. And this probably fits in that category because nobody else makes this much of heavy water. Okay, so 2 groups have been set up, but we are trying to look at what this can do, and one of the obvious things is that you can measure the day-night effect. That means how the neutrinos, what the neutrino numbers are as a function of energy in the day and the night. And if you are more or less equatorial, then or close to the equator, then you get the core effect, which is reasonably large. So you have a better chance of seeing this as compared to perhaps things which are at higher latitudes. And we could also look at the survival probability of electron neutrinos in a region which is being unexplored right now, 2 to 5 MeV. And this will tell us something about beyond standard model theories. Importantly, it can also measure all kinds of neutrinos. It can measure nu e bar because it has a neutron and a proton through the charge current interaction. It also can be broken up by any kind of neutrino. So you can break it up using an electron type, muon type, tau type of neutrino. So it's through the neutron current interaction, it is sensitive to all neutrinos. So it's a kind of versatile neutrino detector. So there's a paper specifically targeting the supernova neutrinos, but we are also working on the physics of solar neutrinos using this. And okay, this is the day-night effect, and specifically the survival probability in this region is very poorly measured. And this could be measured using DLS, which I think this is just 1 year of data if I am not mistaken. Okay, so it's very precise, and the more years you will make this much more precise. You can even bin it in maybe 3 bins, and you can get a very good measure of that. How this is for this so-called standard paradigm, the Mikhail Smirnov paradigm, Wolfenstein paradigm, and for so-called non-standard interactions. And the DLS also can be done. Okay, so what is the outlook? There are many opportunities coming up in nuclear physics, low energy accelerators, better particle detectors, whatnot. Technology is always improving. There is also this possibility of a deep underground facility, deeper than what we are targeting right now at Theni, which can house experiments on neutrinos, dark matter, neutrinoless double beta decay. It can also house a low energy accelerator. And by the way, there is now serious proposals coming up in the next few days. On the 6th and 7th, we'll hear them. 3 groups are actually going to, and probably they will combine to propose a low energy accelerator for making cross section measurements near the so-called gamma peak, which is important for reactions going on in stars. Also seismic measurements. There are also apparently some biology experiments that are proposals that have already been made in very low muon background setup. Perhaps one day even a gravitational wave detector. Indeed, there is an underground detector of which Kajita is the spokesperson for in an underground lab. So who knows, there might be a compact gravitational wave detector someday in this RT particle. So with this, I think I would like to acknowledge the help and collaboration, especially Deepak Chakravarti has been my close friend and collaborator, and many others, including Murthy, Indumati, engineers from BIRC, Govindo Majumdar, Mandal, Vandana, Vasudev, many our students, Mitali, Neha, and many other students. And of course, again, I should say that I have learned a lot from my teacher, CVK Baba. Thank you.
So thank you very much, Vivek. It's such a broad sweep that we had from starting from 1976 onwards. So we have time for a few questions. Just put your hand up and this mic will come to you. Yes.
Hello. Okay. So, sir, you shown result on axion on slide number 13.
Yes.
So there were like backgrounds there, and there were some. There were one peak there. What is that? I missed that. Sorry.
Yeah.
13 probably.
Okay.
So in the right.
Talking about this peak?
Yeah. So
Okay. So this is coming from cobalt some peak. Okay. So this is, there are two cascade of 1.17 and 1.33. In nuclear physics labs, you actually use this cobalt 60 as a source to calibrate your detector, energy calibrate your detector. Also, they are in prompt coincidence, so you can also make some coincidence measurements and find out the time response and things like that. So this happens to be there on the floor of the hall where we were working, and so it was there in the paint. So they had actually painted out this thing. So cobalt comes from irradiation of steam due to leaks and so on. This falls and then this is painted over by this. So it's actually quite a dirty place. We couldn't work here for more than 2 hours before our quota of radiation dose was up. So whatever we had to do, we had to put up the lead shield. Okay, today we make maybe 1/4 of the lead shield go away, come again next day, again, and then that's how it went. So this thing took about a month or so of setting up. But yeah, this is due to a source, cobalt source. In fact, there is also cesium, but cesium is only one gamma ray, so it comes in singles. Our trigger was a coincidence between these two detectors, so it won't come in that.
also you shown that the mass range is between 2.3 to 2.5 MeV.
Yes.
So why it is like that, and why axion should be in this mass range particularly?
No, this is just background. This is due to Compton scattered background. So you can have a Compton scattering of one gamma ray and one detector Compton scattering of the other, and that will give you a prompt coincidence. So when you sum up these two energies, that will sum anywhere between the Compton edge of 1 to 0. Yeah. Why? Oh, that is because of the binding energy. So the idea is that in thermal neutron capture by a proton, you release the binding energy, right?
Okay.
2.2 MeV. Okay, if you want to go to more decimal places, you can go. And then that, instead of a gamma ray being emitted, which is what happens with some 330 milliband cross section, you can emit an axion also with a certain branching ratio. Okay, so if an axion is emitted, it can decay into 2 gamma rays. But the sum energy should still be that, because the deuteron will take away very little recoil energy. Deuteron is 2 GeV in mass, right? So this few hundred keV, no problem. It won't take much of a recoil.
But the QCD axion lie in the mass range should be mass of QCD axion should be below electron volt. So why you?
No. That's what we now have inferred. At that time, if for instance this the so-called standard axion was supposed to be hundreds of keV, and we were looking for that. We didn't find it. So probably this standard axion doesn't exist. I mean, it could be also that the coupling is extremely small, but that's far-fetched. I think it is more likely that it is much lighter axion, and so now people are looking for the light axion. So they are looking at it in the low X-ray energy region and so on, or converting photons to axions, things like that, or axion to photon. All kinds of things are being known. Then you look for it in as resonances in resonant cavities. There are all kinds of ways of looking for this.
Yeah, just one last question.
Yeah, sure.
So axion has a coupling with the electron as well. So and it is in MeV mass range, so it can goes to 2 electrons. That's
So if it has a mass beyond the sum of masses of electron positron, yes, it can go into electron positron as well. That's right.
And here it is the case
So
actually.
in this particular case, we were looking for axion masses below 1 MeV. Okay. If it went into E plus E minus, then you won't get 2 gamma rays, right? So it would lead to something, but we are not sensitive to that.
But why, the decay rate should be higher for the gamma case, rather than electron positron case?
No, it's just that we are looking for axions with masses below 1 MeV. And see, once it goes above the E plus E minus threshold, I think that wins. So it then decays more by E plus E minus rather than by gamma rays.
But phase space allow more for...
There will be some
gamma
branching, no
rays,
doubt,
right?
but this will lose out. Huh? Yeah, that's right. Yeah. Sorry, you were asking something else?
So what I was saying, like the more phase space available for gamma decay than electron positron, and if only if the coupling is larger in one case than other, like let's say axion electron positron coupling is higher.
Yeah, but even if it goes to E plus E minus, there will be some virtual photon which will then decay to E plus E minus. Right? I mean, I'm sure that diagram will be there. So I don't see how it's coupling to the electromagnetic field. It's just that it depends on the mass of the axion. If the mass is low, it can't decay into E plus E minus. If it is high, it can. And just like in the case of strong interactions, once the alpha channel opens up, then that is it. You have a very small branch of gamma. And of course, in some situations, you might want to look at it for other reasons, but that's a different matter. But if you want to look for that particle, you better look for the strongest channel into which it decays. So that's the logic.
So a priori, we don't know what channel it goes for because we don't know what is the axion photon coupling and axion electron coupling. So it could go to any channel, and and due to
we have looked for it in this channel, we don't find it. Okay, now it can decay into some other channels. You have to look for that then specifically. Yeah?
Okay, thank you, sir.
Sure.
Any other question?
There is a question online from Y. Chandrabhan. So he says that thanks for inspiring talk. Please elaborate on nuclear astrophysics studies facility.
Okay. So you see, in stars, these reactions take place at typically 10 keV temperatures to about 100, maybe a few hundred keV temperatures. Okay. So it means that you have to do these reactions at very low energies. And this means that because of the Coulomb barrier of between, when any proton interacts with any nucleus, there is a Coulomb barrier, right? And if you are talking about very low energies, then the cross section drops because the tunneling probability drops. So these things have to be done in, you have to measure very small cross sections. So it depends, of course, on the reaction that you are studying. But typically in radiative transitions, you have backgrounds due to cosmic muons. So you have to go underground. That's number one. Then there are other things that you might have some other backgrounds coming in from impurities in targets and so on. So you might have to build recoil mass separators for that. You might need gas jet targets. So these are all techniques that people use to measure these cross sections which are relevant to the reactions that are going on in the interiors of stars. So you have to go to low energies, and these cross section measurements are difficult. Does that answer his question? I don't know, maybe if he has maybe at some stage if he writes another comment, then we can go ahead. I hope this answers his question.
I have a sorry. It's a general question. So you showed so many different kinds of experiments. So do you get the idea and then decide what equipment you need for it, or because you have some equipment you decide to go in a certain direction? Is there a kind of a way of
a little bit of both. If it requires something that requires a 100 GeV accelerator, then obviously you can't do it here, right? So you try to manage within your means, but you try to do something which is interesting. I mean, there are also I can do a series of elastic scattering measurements, and you can build on that data. You can get some handle on the nuclear optical potential, or you can do a series of transfer measurements and so on. I think the level density thing was the one which we attacked the most. Initially it appeared to be a bread and butter experiment, but when we saw this bump which couldn't be explained, first we thought it was an artifact, but then okay, we tried to. That is the only set I think where we did many experiments in the same way. Otherwise I think we generally like to do some things which are different. So yeah, it depends on what you have and also what you can build, because if it going to take 10 years to build, ICAL is one of those types. But you also have to be productive, so you have to do also experiments that produce some result, and not just a trivial result. I mean, so I think most of these experiments, I would guess, are at least interesting. They may not be, Nobel Prize winning, but they are at least interesting. So, and they are different. So, it is a mix and match of both. What you can think of and what you can do. Because experiments, of course, involve something that you should be able to do it. You know, you just thinking about something, it can be done. Oh, that, I leave that privilege to theorists, but experimenters have to deal with things that you can do. So you can't, think of something. Sorry? Yeah?
There was a low blow.
No. I didn't mean it as a low. I mean, theorists, of course, have this freedom of going anywhere in the universe. Small, large, everything. But, I mean, experimenters, and especially, well, if you think of some good experiment, of course you can propose it and to get it done elsewhere, but you would like to do it here if possible, and so you would like to think of experiment that can be done here, and but at the same time are not boring. So we have tried to do a little bit of both. And I hope, I hope I have conveyed that there are many possibilities for the future. This DLS really excites me. The deuterium has a neutron and a proton, so it's a simple object. But it can allow you to measure neutrinos, antineutrinos, all types.
And the greatest advantage is that we are the largest producer of
heavy
water.
So it gives you an unnatural advantage over
everybody
others. Of course, somebody was also saying, maybe it was a cynical comment, that, oh, better not tell this to the Chinese. The Chinese will buy you out. They will buy all your heavy water and do the experiment, if they think it is important, of course. Yeah, but so you try to build on your strength rather than,
And
but in all this, you would have noticed that there are many things that we would really have liked if there are nuclear theorists of the caliber of, for instance, Chindu Varke. I mean, in the 60s and 70s, there were many good nuclear theorists all over. PRL, IOP, TIFR, DRC even. But slowly their numbers dwindled, and now they are almost in the, what is that? In the case of animals, you have this name. Endangered species. They are in the endangered list now. So, that bump, for instance, that is something that could have been explained by our own colleagues. But there were not enough theoreticians around to get excited by that. Unfortunate. Of course, in the case of berylliumite, we could get a theoretician through the new communication channels that we have, and he was quite excited by it, and he did the computation for us. So now, of course, maybe the theorist can be anywhere. If he gets excited by what you do, it can be done, perhaps.
Okay, I think we'll stop here.